Welcome to the part 14 of the session 1 of real analysis. So, in this session, we will be discussing what are nested intervals. In the previous session, we have discussed what are intervals and we have learned how to characterize a subset of real numbers to be an interval. In this class, we will be discussing what are nested intervals. A sequence in for n element of n is said to be nested if I1 contains I2, contains etc., contains in plus 1, contains etc. So, we can see a geometrical approach to visualize this. A sequence in of intervals is said to be nested if I1 contains I2, contains I3 and so on. So, let I1 be an interval, we are considering without laws of generality open intervals in this case. So, suppose I1 is the interval open interval A1 B1 and I2 is the open interval A2 B2. What do we have is the interval I1 has the endpoints A1 B1. It contains I2 means the endpoints of I2 should be inside the interval A1 B1. So, we have A2 and B2 like this, A3 and B3 follows and so on. We have our AN, BN something like this. So, that is why it is called a nested sequence of intervals, because it encloses all the intervals inside it. That is why it is called a nested sequence of intervals. So, such a sequence of intervals is what is called nested. Then we can see some of the examples. Let In is equal to the closed intervals 0, 1 by n. Then prove that the intersection of all such intervals is nothing but the singleton set 0. So, let us see, we have the interval In is equal to the closed interval 0 to 1 by n, and therefore, what is I1? I1 will be 0 to 1. We have I2 to be equal to 0, 1 by 2, I3 will be equal to 0, 1 by 3 and so on. So, if we draw the geometrically the set of all these numbers, we have 0, 1 somewhere here, then we have 1 by 2, then we have 1 by 3 and it is approaching like this. So, the first interval is 0 to 1, the second interval is 0 to half, the third is 0 to 1 by 3. So, we can see that all these numbers which are the upper bounds of this set, each set In, this 1 by n is approaching to 0 as n is approaching to infinity. So, we can see that this is approaching to the set singleton set 0. And we can see that these are nested intervals, because I1 contains I2, contains I3, the intervals are becoming smaller and smaller, and finally, as n approaches infinity, we will be getting a singleton set 0. That is why we have the intersection as singleton set 0 in this case. Now, let us consider another example in which we have In is equal to open interval 0 to 1 by n. Then we can show that the intersection of such intervals is the empty set, because there is nothing in common. Why? Because in the previous case 0 was included in each of the intervals, but in the next case we have In is equal to the set of all open intervals 0 to 1 by n. So, proceeding as we have done in the previous case, we have I1 equal to 0 to 1, I2 equal to 0 to 1 by 2, I3 is equal to 0 to 1 by 3, but none of these intervals contain the element 0. So, as n approaches infinity, this side is going to be equal to 0 as well, and we have nothing in common. I1 intersection I2 etc. will be equal to the empty set, because we cannot have anything in common if we intersect it up to infinity, because 0 is not included. So, that is the proof of this result. And the next is again In is an open interval n to infinity. So, this is an interval which is not bounded from above, but it is bounded from below. We have to show that this is also a nested interval, but the intersection is equal to null set. So, let us first see whether it is a nested interval. We are given In equal to open n up to infinity. Therefore, what is I1? I1 is equal to 1 to infinity. I2 will be equal to 2 to infinity, which is included inside this I1. I3 is equal to open interval 3 to infinity, and so on. But when we draw the pictorial representation, we can see 1 to infinity, then 2 to infinity, then 3 to infinity, and so on. When you take the intersection of all this up to infinity, we are getting it as an empty set. There is nothing in common, because each set has deleted some of the terms from the previous ones. So, the intersection of all those becomes equal to null set. So, that is how we prove that intersection In equal to 1 to infinity, In is equal to null set. The next is a very important property in real analysis, which is called the nested intervals property. If In is equal to the intervals a n b n is a nested sequence of closed bounded intervals, definitely there exists a point C belonging to R such that C belongs to In for every n belonging to n. So, that answers the previous questions that we had, because in these two examples we were having open intervals 0 1 by n, which gave you intersection as null set. So, in this theorem we are defining a condition under which a nested sequence of intervals do possess a common element. So, the condition is that, or nested interval property states that, if In is equal to closed interval a n b n is a nested sequence of closed bounded intervals, definitely there exists a common element C in R such that C belongs to In for every n element of n. So, let us look at the proof of this. We are given In is equal to, we are looking at the proof. So, In is equal to the closed interval a n b n is a nested sequence of intervals, which means I1 contains I2, contains etc., contains In, contains In plus 1, and so on. Okay. So, this is the condition for nested sequence of intervals. Then, if we consider the geometrical viewpoint of these intervals, we can see, as we have drawn previously, this is A1, this is B1, inside you have your A2, B2, and this goes on like this. So, somewhere here is your AN and BN, and so on. So, if you take the set of all the left endpoints of these intervals, we can see that they are bounded above. And if you take the set of all the right endpoints, we can say that they are bounded from below. So, that is the main point in which the proof is based on. So, you take the collection AN where n belongs to the set of all natural numbers. This is a bounded subset of R. This is bounded above. This is bounded above because we have so many right endpoints which are on the right side of this. So, it is bounded because I1 contains all this, definitely it is bounded above at least by B1. So, definitely it has an upper bound, and so by supremum property ensures that there exists at least one point C which is called the supremum of this set AN where n belongs to the set of all natural numbers n. So, because C is the supremum, we have now the condition that AN is less than or equal to C for every AN. Now, it remains to show that C is less than or equal to Bn for every n. Then definitely C is inside each and every one of these intervals because they are nested, and hence C is the common element in the intersection. So, there we apply the next condition. So, we have to show that C is less than or equal to Bn for every n. So, now two cases arise. Which are the two cases? Because we have A1 is less than or equal to B1 definitely, and since these are nested intervals, A2, B2 is contained inside A1, B1, but we have to ensure that B2 is an upper bound of A1 and A2. Similarly, Bn is an upper bound of A1, A2, etc. up to An. So, that is to be proved. That is what remains to be proved. So, we have to consider two cases. Case 1, so C is less than or equal to Bn has to be proved in this way. We have C to be the supremum of An, and in order to have C less than or equal to Bn, it suffices to prove that Bn is an upper bound of the set An. So, that is enough. We will be getting the condition that C is less than or equal to Bn. So, the case 1 is we are taking some k less than n. Suppose you take k to be less than n, we have Ik contains In. Why? Because we can see that I1 contains I2, contains I3. So, as the surfaces become larger and larger, the intervals are becoming smaller and smaller. So, if you have k less than n, Ik contains In, Ik becomes the larger interval than In. Therefore, we have the closed interval AK BK contains the closed interval AN BN, which indicates that AN BN is somewhere here, AK BK is contained inside this. So, what happens? Bn lies to the right side of all these elements, and therefore, since An is less than or equal to An less than or equal to AK, An less than AK less than BK less than Bn, which shows that An is definitely bounded above by Bn. So, we have Bn is an upper bound of the set An, or AK you can take. AK is bounded above by Bn, whatever it be you can have, it is an upper bound of the set AK. Now case 2, what is case 2? We have case 2 shows that we have taken k to be less than n here. Now we are taking the case when k is greater than or equal to n. So when k is greater than or equal to n, then what happens? N becomes less than or equal to k. That is in contains ik, because n is the smaller suffix. So in contains ik, which means akbk is contained fully inside an bn. So again we have what? So this also shows that the set of all an is bounded above by bn. Therefore, in both the cases, bn is an upper bound of the set of all left sides an. Here an does not mean the endpoint of one particular interval. It indicates that it is the upper bound of every such an's, and so C being the supremum, C is less than or equal to bn, and this is true for every n. Therefore, we have an less than or equal to C less than or equal to bn for every n, which indicates that C is in the intersection of all the intervals. So that is proved. So that proves the nested interval property. And does it ensure that there is only a single point C belonging to such R which is belonging to all the INs? That need not be the case, because if we consider the nested intervals like this, nested intervals if we consider, I1 is this one, I2 is inside, I3 is inside, and so on. We keep on going like this. We can see that the left side may end at this point and the right side may end at this point. So there can be many points between the, or many points which are included in the intersection part. So these are the left endpoints A1, A2, etc., and these are the right endpoints B1, B2, etc. So the proof that we have seen just now ensures that there exists at least one point, but it need not exactly say that that point we are having is unique. So there can be any number of points inside the intervals. Now, what ensures that the point that is common becomes a unique point? That is what we can see in the next slide. We are having a result. If In is equal to An Bn is a nested sequence of closed bounded intervals as we had in the previous case, and additionally we have one more property, that infimum of Bn minus An should be exactly equal to 0. Then there exists a number C in In such that that number is unique. So the length of the intervals should become very small. Infimum of the lengths should be equal to 0. So that is what we are going to see. The proof is exactly similar to the previous one. Only thing is that, only difference is that we have taken C to be the supremum of the set of all An, and similarly a similar argument can be applied to show that if D is the infimum of Bn, then both C and D belongs to In for every n. So we have C and D belongs to In for every n by nested interval property. A similar argument as we have seen in the case of nested interval property ensures that these two belongs to In for every n. But the length of In is equal to Bn minus An has infimum of Bn minus An equal to 0. So that means if D minus C is having a positive length, the infimum of this cannot be equal to 0. So, this indicates that this forces our C to be equal to D, and hence we have a single point which is the supremum of all the left sides as well as the infimum of all the right sides. And that ensures that the common point will be a unique common point. So, the nested interval property ensures that for all the closed bounded intervals which are nested do have something in common, and if the lengths of the intervals are becoming smaller and smaller and finally it becomes 0, then the number will become a unique number. A similar result can be proved or can be used to show that the set of all real numbers is countable, is uncountable. So, the set of all real numbers is uncountable can be proved using the nested interval property. Let us see how we can do this. We have to show that the set of all real numbers is uncountable. So, in order to prove that something is uncountable, if possible, let us assume that it is countable. So, if possible, we assume R is countable, and hence we can arrange what is a countable set? The countable set is a set which is either finite or denumerable. We have seen in an earlier session, and so there exists a bijection from the set of all natural numbers to the set R. There exists a bijection from the set of all natural numbers to the set of all real numbers, because our assumption is that R is countable. Or in other words, we can enumerate the elements of R as an interval, say I1, which is equal to x1, x2, x3, etc. Because R is countable, we can write the numbers of R as x1, x2, x3, etc. We are defining it as an interval I1. Now, from I1, we are going to define a new interval I2. I2 is an interval which is obtained from I1, but it does not contain the first point x1. So, I2 is the interval x2, x3, etc. So, definitely I2 is contained in I1, but x1 is not included. x1 is not an element of I2. Similarly, we define I3 to be the set of all elements x3, x4, etc. by excluding the element x2 from I2. So, x2 is not an element of I3, but I3 is contained inside I2. Likewise, if we move on, we can see that these are all enumerated, and they are closed bounded intervals as well, that we will be dealing in later classes why they are becoming closed and bounded. So, they are all closed bounded intervals because R is countable we have taken. So, the nested interval property ensures that these I1 containing I2, containing I3, containing etc. should have something in common. So, we have some C belonging to the intersection of INs for n equal to 1 to infinity by nested interval property. But then what happens? Can C be equal to I1? No. Sorry, x1. C is not equal to x1. Why? Because C cannot be in I2, I3 and so on, because we have excluded x1 from I2. C cannot be equal to x2 because x2 is excluded from I3. So, it cannot be in the intersection. and likewise it cannot be any of these listed in this enumeration. So, we have a common point which is not in the listed set of elements, and that shows exactly why our assumption is wrong, and we have R is an uncountable set. Therefore, the nested interval property can be used to show that the set of all real numbers is uncountable. So, in this session, what we have discussed so far is, we have seen what are nested intervals, when do nested intervals have something in common. We have seen that for open nested intervals, it does not have anything in common, the intersection is equal to null set. Whereas, if it is a closed finite interval or closed bounded interval, they do possess something in common. And we have seen what is nested interval property, which shows that if In is equal to An Bn is a nested sequence of closed bounded intervals, there exists a common element C belonging to R, and if the interval infimum of Bn minus An or the length of the intervals is reducing and the lower bound or greatest lower bound is equal to 0, then the number C will be a unique number, and this is used to show that the set of all real numbers is uncountable as well. So, with all this, we have seen what are the algebraic properties of R, the order properties of R, intervals in R, different subsets of R, and nested property of R or intervals. And from this, we ensure that the set of all real numbers cannot be countable, the set of all rational numbers is countable, but the set of all real numbers remains to be uncountable because of the presence of the irrational numbers. So, in the next coming sessions, we will be discussing more on real numbers, and that is for today. Thank you.